In this video, we will see some problems based on mutual inductance. These are actually examination problems. The flux linked with a large circular coil. The flux linked with a large circular coil of radius r is 0.5 into 10 to the power minus 3 Weber or 0.5 milliweber. 0.5 milliweber. When a current of 0.5 ampere, flows through a small neighboring coil of radius small r. Flows through a small neighboring coil of radius small r. Calculate the coefficient of mutual inductance. Calculate the coefficient of mutual inductance for the given pair of coils. Also, this another part. If the current through the small coil suddenly falls to zero, if the current through the small coil suddenly falls to zero, what would be its effect on the larger coil? What would be its effect in the larger coil? Okay, so let me read this. The flux linked with the coil or with a larger coil of radius r is 0.5 milliweber when a current of 0.5 ampere flows through a small neighboring coil of radius r. Calculate the coefficient of mutual inductance for the given pair of coils. If the current through the small coil suddenly falls to zero, what would be its effect in the larger coil? Now first we will try to understand what is given here. We are given with two coils of different radii. So one small coil has its radius r1 and we have another coil of bigger radius. Now the flux which is there is a current flowing when a current 0.5 ampere flows through a neighboring coil of radius r. So there is a current flowing through this coil. This is switch I'll mark, and the current through this is 5 ampere. So this produces a flux and that flux links the second coil also. Let me say the second coil is connected to the galvanometer. The flux is 0.5 milliweber. Calculate the coefficient of mutual inductance. So let me say the current given, the current in the coil or in the first coil, you can write, or what I will do is I'll mark these coils as coil 1 and coil 2, or you can take it as coil with radius r and coil with radius capital R. So current in the coil of radius r as I1 equal to 5 ampere. So I will take this as I1. Current in the coil of radius small r as 5 ampere. Now flux linked with the larger coil is flux linking the larger coil as given phi 2 equal to 0.5 milliweber. Now by definition, M as phi 2 by I1. Total flux linking coil 2 due to current in coil 1. So it is phi 2 by I1. Now calculate this, and how much are we going to get? 0.5 into 10 to the power minus 3, 0.5 into 10 to the power minus 3 divided by 5. So this will be equal to 5 ampere, right? The current is 5 ampere. How much is the current? Sorry, 0.5 ampere only. The current is also 0.5 ampere. Sorry, just correct it. I1 is 0.5 ampere. So I made a mistake here. The given value of current is 0.5 ampere, not 5 ampere. Please do correct it. The given current is not 5 ampere, 0.5 ampere. Make a note of it. Divided by 0.5. So this is 1 into 10 to the power minus 3 Henry. So very simple. M as 1 millihenry. M is 1 millihenry. So mutual inductance of two coils is 1 millihenry. The second question is, if the current through the small coil suddenly falls to 0, what would be its effect in the larger coil? So we know that when the current falls suddenly to 0, the flux also will fall to 0. That means the flux also decreases quickly, and hence there gets an EMF induced in both the coils. But you have to write only for the larger coil. So with the fall of current in smaller coil, the magnetic flux linked with larger coil decreases to 0 quickly, which in turn produces large induced EMF in the second coil or in the larger coil. So you can write here, because we know the change of current causes change in flux, and when there is a change in flux, there gets an EMF induced in the coil. With the fall of current in smaller coil, the magnetic flux linked with larger coil also decreases. With the fall of current in the smaller coil, the magnetic flux linked with larger coil also decreases. Due to this, an EMF gets induced in the larger coil. And because you can also add one more sentence, because the current decreases to 0 quickly, there is a large amount of EMF induced. So also the current in the smaller coil falls quickly to 0. Also, the current in a smaller coil falls quickly to 0, comma, the magnetic flux, the flux linking the larger coil decreases to 0 quickly, and hence there is a large induced, and hence, or you can write 0 quickly, which in turn produces large amount of EMF in the larger coil. Also, given that the current in the smaller coil falls quickly to 0, the flux linking the larger coil decreases to 0 quickly, which in turn produces large amount of EMF in the larger coil. Now, hope you understood this. You can take down another problem similar to this. A large circular coil of radius r and a small circular coil of radius r are put in vicinity of each other. If the coefficient of mutual induction for this pair is 1 millihenry, if the coefficient of mutual induction for this pair is 1 millihenry, what would be the flux linked with the larger coil when a current of 0.5 ampere flows through the smaller coil. Okay, so we'll read it once. A large coil of radius r and a small coil of radius r are put in vicinity of each other. If the coefficient of mutual induction for this pair is 1 millihenry, what would be the flux linked with the larger coil when a current of 0.5 ampere flows through the smaller coil? Now, first list out the given quantities. Given mutual inductance M for both the coils is 1 millihenry. Now, also given current through smaller coil I1 is 0.5 ampere. Now, what is the flux linking the second coil? you have to calculate what is the flux linking the larger coil. Phi 2 is what? Now this is a direct application of the formula. You know phi 2 is m into I1, or m is phi 2 by I1, or phi 2 is m into I1, and m is 1 into 10 to the power minus 3 into 0.5. The value is 0.5 into 10 to the power minus 3 Webers. Or 0.5 milliweber. Phi 2 is 0.5 milliweber. So the flux linking the larger coil is 0.5 milliweber. Milliweber. Okay.